this exercise continues along the same lines as the previous few exercises in terms of using image convolution to extract or isolate features from an image. But now we are going to be using a different set of kernels to extract different kinds of features. In particular, we are going to use a vertically oriented kernel and a horizontally oriented kernel. Now, this might look like stripes, but in fact, each of these is a 3 by 3 matrix. So you can see the three increments here, indices here. So these are 3 by 3 matrices, but here all of the columns have exactly the same value, and here all the rows have exactly the same value. You can also see that these kernels are quite a bit smaller than the Gaussian kernels that we used in the previous few exercises for smoothing. In fact, I mentioned in the video for the previous exercise that a 31 by 31 kernel is really big. It slows down the convolution quite a bit. So this is more typical for like real world applications. The kernels tend to be small, 3 by 3, 5 by 5, maybe 7 by 7, but even that is starting to get a little bit on the big side. It's the trade-off, of course. If the images are small, then the kernels can be bigger, but if the images are small, you don't really need such big kernels. The bigger the image, the longer it's going to take with convolution. And there are tricks to speed it up, like a parameter called stride, for example, where you're not running convolution at every single pixel, but skipping by a few pixels. That's stuff you would learn about in a computational image processing or computational vision course. Anyway, so we are going to run convolution with these two kernels and see what the results look like. Now, you can do this with the three-dimensional version of the bathtub image by convolving each layer, each color channel separately. But in my code for this exercise, I just did it on the two-dimensional image just to make it a little bit simpler, just for convenience, basically. Okay, so now I'll switch to Python. I will show you the code and I'll show you what the results look like. Here you see the two kernels, by the way. This is the vertical kernel and the horizontal kernel. Super duper simple. It's a very straightforward kernel. It's just, ones, zeros, and minus ones, and here they are oriented the other way around. By the way, little thought experiment for you. What is the rank of this matrix and what is the rank of this matrix? Do you have an answer yet? You can pause the video if you would like some more time to think about it. The rank is 1 in both of these cases. These are rank 1 matrices because every column can be expressed as a linear combination of other columns. So this column is 0 times this column, and this column is minus 1 times this column. So these are both rank 1 matrices. Okay, so let me run this code. And then, I think the conceptual part of this exercise is more interesting. The code itself is not so interesting. So let's see. That's just because you've seen all of this code before. Okay, so here we have convolution with the vertical kernel and here with the horizontal kernel. And this is really interesting to compare. So here, when you look at the buildings, you see these really sharp vertical lines. You do see some horizontal lines, but actually when you look carefully, these are not purely horizontal. They're a little bit angled, but the vertical lines are really sharp that you see on this building as well. And then when you look at the result of convolution with the horizontal kernel, you see that all of these vertical lines basically disappear, right? That's very striking here on the building on the right side and here. And on the bathtub, you see these really strong, these are telephone poles here, and they're almost invisible here. And this building over here to the left, here you see vertical lines, and here you don't see any vertical lines. Okay, and then, as I mentioned, you do see these diagonal lines here, but that's because a diagonal line is a combination of a vertical line and a horizontal line. So it's a little bit horizontal and a little bit diagonal, and so the diagonal component of, the vertical component of the diagonal line is preserved here, and the horizontal component of the diagonal line is preserved here. So these kinds of kernels are used all the time for image recognition, image processing, edge detection. For example, they're used in X-ray machines at airports to detect for sharp edges that might be indicative of weapons. So if you enjoyed working through this, then there's so much interesting stuff you can do. You can take these three kernels. So now we've had three kernels, the Gaussian and the vertical and the horizontal. And we have three color channels. So you can smooth the red channel and do vertical kernel for the green channel and horizontal for the blue channel. I have no idea what that would look like, but it would probably look pretty kooky, a little weird. And yeah, you should try it and see how it works.